Let's take a look at this problem. To find all primes p and q such that p squared divides q cubed plus 1 and q squared divides p cubed plus 1. Before we move on, don't forget to give a like, subscribe to my channel, and turn on post notifications. Two things came to my mind when I first saw this problem. The first one is that the two expressions are symmetrical, which means that if I swap the positions of p and q, the statement is still the same. So I can say that by symmetry, or with the loss of generality, in short, W log, I can say that P is the larger number. Then from this, I can pick to consider P squared divides Q cubed plus 1. The reason that I picked this expression to consider is that it seems that I'm going to achieve more, but considering the fact that a smaller number is divisible by a larger number, this can tell me, this can give more information. This is followed by p squared divides q plus 1 times q squared minus q plus 1. So I factorize the dividend because it's just sum of cubes. Then the second, I'm going to use the second thing that came to my mind, which is the Euclidean algorithm, which says that whenever I divide some number, so for a, it's actually the dividend, and then b is the divisor, then q is the quotient, and r is the remainder. Of course, I'm going to specify that the remainder is between 0 and b. It cannot be equal to b because in that case, I can just add 1 to the quotient. Then for the GCD of a and b, GCD, and the full name is the greatest common divisor of a and b, is actually equal to the greatest common divisor of r and b. So this is the way we calculate the greatest common divisor of two large numbers, because I can say that GCD is equal to the GCD of another two numbers, with one of them being the remainder after division. So the numbers start to keeps decreasing, and eventually we will obtain two numbers that we can calculate with our mind, or it's just becomes much more obvious. So back to our main problem. Now I'm going to consider the GCD of q plus 1 and q squared minus q plus 1. The reason that I'm going to consider this is that I'm trying to analyze whether p divides just exactly one of them, or p is going to divide both of them. So the greatest common divisor of these two numbers is very important. So I'm going to apply the Euclidean algorithm by dividing q squared minus q plus 1 by q plus 1. So you may choose to use a very primitive way, which is long division, treating terms with different degree as in like digits, and do the long division. Or you may quickly observe that the quadratic expression is actually equal to q plus 1 times q minus 2 plus 3. You can also obtain this by doing the long division. Like you put a q here, and then subtract, you get minus 2q, and then you add minus 2 as the final term of the quotient, and the remainder is 3. So that means it's actually equal to the greatest common divisor of 3 and q plus 1. And you know that this so-called GCD must divide 3, so it means it must be either 1 or 3. But we're not going to divide the cases into in this way. I'm going to consider cases separating situations when whether P divides both expressions or P just divides one of them. So if P divides both Q plus 1 and Q squared minus Q plus 1 as well, then surely P must divide its greatest common divisor, because you can the so-called GCD can be worked backwards and to be rewritten as a linear combination of the two numbers. So that means P divides 3. Well, if a prime divides 3, then surely we know that P equals to 3. Now, given this information, we can say that Q squared divides 3 cubed plus 1, putting back into the other expression. So that means Q squared divides 28, and we know that 28 is equal to 2 squared times 7. So the only possibility for that to happen is that Q equals 2. So we've obtained some solutions. Now, to our second case, which is just the opposite. Otherwise, well, because P squared has to divide Q cubed plus 1, then P squared must divide exactly one of them. Well, this is the otherwise case. So if it cannot divide both expressions, then it must divide exactly one of Q plus 1 and Q squared minus Q plus 1. However, this is impossible because P is a larger prime. Is larger than Q. So P squared is at least equal to Q squared. Now Q squared is apparently greater than both Q plus 1 and Q squared minus Q plus 1. So I will write this out formally. This inequality Q squared, to compare Q squared and Q plus 1 will actually fail if Q is equal to 1, but we know that Q must be a prime, so Q is at least 2, so this would work. And finally, Q squared is clearly greater than or equal to Q squared minus Q plus 1. So we cannot have P squared to divide them. I should not even say greater than or equal to, it should be greater. So then the contradiction would hold. So that means I cannot obtain any solution in this case, and I can only get two solutions, which is that P and Q are either 3, 2 or 2, 3. So let's check before we end. P squared equals 9, Q cubed plus 1 equals 9. So P squared divides Q cubed plus 1, take. And then Q squared is 4. And then P cubed plus 1 is 28. So Q squared divides P cubed plus 1, so take. And similar if we reverse the values. So here's our final answer. It's either 2, 3 or 3, 2. I hope you enjoyed the video. Feel free to suggest any alternatives in the comments. If you like my videos, make sure to subscribe to my channel right now. Thank you for your support. See you next time.